In this video, we're going to look at structural isomers in organic chemistry. We're going to cover it in quite a bit of detail and go through some examples. So it's a good idea to make some notes as you're going along to help you remember what we're covering. Let's just start with our definition of structural isomers, which seems usually quite a simple, nice, easy definition to do. We want to keep it simple. Structural isomers have the same molecular formula and a different structural formula. Although it's a relatively simple definition, it's really specific, and because of that I've underlined the most important words about what is the same about them and about what is different. So what we don't want to do is just say the same molecule. They're not the same molecule, they are entirely different molecules. We do not want to say the same formula because we talk about lots of different types of formula: molecular, general formula, empirical formula, structural, skeletal, etc. There's lots of different ways we can represent molecules. You could say that they have a different structure if you prefer, because that is also true. If they have a different structure, then they have a different structural formula. Don't say, however, just different arrangement of atoms. That's not quite enough, and that's because it's too similar to our later definition of stereoisomers, where we talk about a different relationship or a different arrangement of atoms in space compared to each other, and it's not the same thing as a structural isomer. And don't forget that people think about, oh, you know, are all of these molecules isomers of pentane or isomers of octane? There's no such thing as, there's not like this one main molecule and then everything else is an isomer. It's simply for any given number of atoms, like 5 carbons, 12 hydrogens, there are a particular different number of ways we can arrange them and join them together, and they are each isomers. So you can think of an isomer, the word isomer, as being like the word sibling. You can't have one sibling. You basically, siblings are related to each other, and isomers are related to each other based on their molecular formula. And there are 3 types of structural isomer, which we're going to have a look at now, which is chain isomerism, position, and functional group isomerism. So chain isomers are the first type of structural isomer, and we tend to call them branched isomers sometimes, or carbon skeleton isomers. And they're the first type that we come across. We come across them sometimes even at GCSE level. So for example, these 3 molecules, they all have the same molecular formula of C5H12, and they have different names to distinguish them. So this one is pentane. That's our straight chain isomer. And then we have 2 branched isomers with the formula C5H12. And this one would be called methyl butane, because it's 4 carbons in the main chain with 1 carbon coming off it. And then this third one would be called dimethyl propane. And you may be thinking that we need to have a number to say where the methyl group is. Well, if we look at butane, there's only 4 carbons, so this methyl group can only be on the 2nd carbon in. If I switch it round and try and put it here, that's still the 2nd carbon in the chain, so it's the same molecule. And the same for my dimethyl propane. If this is my main chain of 3 carbons, I can only put the methyl groups in the centre, because otherwise they'd be on the end of the chain and be going back to butane. So for chain isomers, the number of isomers you can have depends on like how many carbons you have, really. And the name of the molecule changes quite obviously, because the main chain gets shorter as you add more branching. So we're going from pentane to butane to propane. And for alkanes, this is the only isomerism they do. So this is the only possibility for an alkane, is to make the chain shorter and introduce more different branches. When you've got different functional groups, however, such as an alkene with a C double bond C. You can now keep the main chain the same length, so in this case 6 carbons long, and you can move the position of the functional group. So we can move the double bond along the molecule. This one here would be called hex 1-ene because the double bond is between the first and the second carbon. This one here would be called hex 2-ene because the double bond is between the second and third, so it starts on the second. And this one here would be hex 3-ene because the double bond is between the third and the fourth carbon. If you've not seen skeletal structures before, it's just showing the carbon skeleton. So if I count 1, 2, 3, 4, 5, 6, that shows me my 6 carbons. I'm not showing the hydrogens, we're just showing the kind of outline of the molecule. You've got to be a little bit careful with moving the position, and remember that molecules can be rotated around. So if I then went, oh, what about hex 4-ene? Well, that is not hex 4-ene because that double bond is between the second and the third carbon, exactly the same as that double bond. And so this is hex 2-ene. And it's not an isomer, it's exactly the same as the one that we've already covered. We just rotated it 180 degrees. So loads of other functional groups can have position isomers. The number of possibilities just depends on the length of the carbon chain and maybe like the number. So if you have 2 double bonds, there's even more options about how you can arrange them. The final type of structural isomerism is functional group isomers. This is not quite as common in terms of questions and things like that. One thing that does come up a lot is alkenes and cycloalkanes. So both of these molecules have the formula C6H12. So compared to an alkane, they have 2 less hydrogens. So if it was hexane, we would have C6H14. For the alkene, the reason for that is because we have a carbon-carbon double bond. So we've taken 2 hydrogens off in those locations to make that bond. And for the cycloalkane, it's because we've joined, doesn't really matter where I do it, 2 carbons together that would otherwise have been at the end of a chain. And if they were at end, they would have had an extra hydrogen each. So again, whenever we make a new bond between carbons, we have to remove hydrogens. Another common example of this is aldehydes and ketones. So the one on the left here is called butanal and the one on the right is called butanone. Don't worry if you've not covered those yet, but you can see they have the same number of carbons and hydrogens. And carboxylic acids and esters are also examples. So both of these would have the molecular formula C4H8O2. So because these isomers have different functional groups, they have very different reactions. So you can look for clues in questions that might eliminate a particular isomer. So if you know it has the formula C6H12, but the question says it doesn't decolorize bromine, then it must be a cycloalkane because all alkenes react with bromine. So you can look for clues like that in the question, and there will often be some, so that you don't end up drawing every single possible isomer that there might be. So we've covered 3 different types of structural isomers. We've covered chain isomers, position isomers, functional group isomers. So don't forget, when you do get a question, if it just says structural isomers, then it could be talking about any of these examples. And there are many formulae. For example, this would all be C5H10, where we have all of these examples going on. So we can have pent 1-ene, and then here is an example where we have pent 2-ene, so that's a position isomer. We could have a functional group isomer where we actually make a cycloalkane instead of an alkene, and then we could of course have our branched chain isomers, given the examples down here where, for example, we could have 3-methylbute-1-ene and 2-methylbute-1-ene. So we've got also some ones there where we move the position of the double bond and we move the position of the methyl group. So lots and lots of different options, even though the formula is quite simple, only 5 carbons. Okay, some tips for identifying isomers or for drawing isomers. Common mistake is drawing the same molecule twice. All of these molecules are the same. They're not isomers, they are just the same thing. And there's no difference except for the direction that they've been drawn in. So to stop you doing this, if you want to know whether you've drawn the same molecule twice, or sometimes they will give you a question where there's a trick where a couple of the molecules are actually the same thing and they're not isomers at all, then there are a couple of things you can do. One is, if you're confident in it, and you should practice it anyway, you can draw the skeletal formula. So if I looked at that first one, it's got 3 carbons. So I go 1, 2, 3, and then I join a bromine onto my third carbon. Now if I was going to draw the next one skeletal, there would be no difference. It's 3 carbons and there's a bromine on that carbon there. And then the other thing that you can do is try to name it. So hopefully you can see all of these molecules contain 3 carbons in a row with a bromine attached to the first carbon in the chain. So they are all 1-bromo propane. In fact, there's only one option of like another isomer with this formula, and that would be 2-bromo propane. The only other thing I could do is move the bromine to the middle. Okay, let's have a look at some example questions as well to see how we can avoid mistakes and avoid, again, not drawing the same molecule twice. In this question, we're told that these molecules are unsaturated structural isomers of C5H10, and later on in the question it goes on to ask you to draw the other 2. So remember we said about clues in the question. One of the clues here is it says unsaturated. So what we're not going to draw is we're not going to draw any cycloalkanes because we've been told that they are unsaturated only. All of our molecules therefore must contain a double bond. It also says structural isomers, so if you've done about EZ and stereoisomers, we can't include that in this question because that would not be an example of a structural isomer. So if we just quickly drew the skeletal formulae and named the isomers we already have, we can see what we've already got, so we don't do any repeats. So the first one's got 1, 2, 3, 4, 5 in a row. There's 5 in a row, and the double bond is between the first 2 carbons on that right hand side, so I could draw that. So that is pent 1-ene, 5 carbons in a row, double bond on the first carbon. The next one is still 5 carbons in a row, so I'm still going to draw that, but this time the double bond starts on the second carbon, moving from the left hand side because that's the smallest number, and so I can put my double bond there, so that one is pent 2-ene. And then the next one does not have 5 carbons in a row, it has 1, 2, 3, 4, and then a CH3 there. So that's going to be bute. It's bute 1-ene because if we look again from the right hand side we can see the double bond starts at the start of the chain. And the methyl group, therefore, if that is carbon number 1, that would be carbon number 2, so it would be 2-methyl bute 1-ene. Okay, so let's see what changes we can make. We've got pent 1-ene and we've got pent 2-ene. We can't have pent 3-ene. If we try to draw a pent 3-ene, so let me just decide to do that skeletal thing again, and I go 1, 2, 3, okay, double bond there. You can see it's actually the same as isomer 2. So there is no pent 3-ene, that is just pent 2-ene because the double bond is between carbon 2 and 3. Okay, so we can't do anything else with pent. We've run out of options for 5 in a row. So maybe if there's something else we can do for butene with 1-methyl group. So there's one option is to keep the double bond in the 1 position, so bute 1-ene, but move the methyl group somewhere else. And don't feel pressured into drawing the molecule like they have. You don't have to follow the same patterns. You can do displayed, you can do the skeletal. It doesn't say, it just says draw the structures. So I'm going to keep the double bond on a 1, but instead of the methyl group being on the 2, I'm going to put it over here on the 3. And obviously if I was drawing this properly, I would include all the hydrogens, but you can see how easily I can come across. That would be but-1-ene, but it's 3-methyl, and that 3 is relative to the 1 where the double bond is. Normally you can't get 3-methyl butane because that would just be on the second carbon, but because we've got a double bond, that gives us a point of reference. So we've tried keeping the double bond in the same place and moving the methyl group, so now we're going to do it the other way round. Keep the methyl group on the 2, but move the double bond between the 2 and the 3. So again, we do 4 in a row, move the double bond between the 2 and the 3, keep the methyl group on the 2, count all the bonds to make sure that each carbon is only making 4 bonds, and that one would be called 2-methyl but-2-ene. So you can see actually it's pretty easy to work stuff out if you just work on moving one thing at a time and keeping other things the same. So isomerism often comes up in short answer multiple choice questions where you might have to identify pairs of isomers, especially from skeletal formulae. So you might get a question like this and be asked which are the isomers, and you might be tempted to sit there and kind of work out from the skeletal formulae, oh, I've got to draw them out. You don't need to do that. So from this example, we can immediately eliminate number 3. And the reason we can do that is number 3 is not cyclic and is not got a double bond in it. So it has extra hydrogen compared to the other 3. So from the others, we just need to count carbon atoms. So remember which skeletal, 1, 2, 3, 4, 5, 6. The next one, hopefully we can see, has 5, and the last one has 6 because it's kind of easy to see the shape, which means that 1 and 4 are the isomers. Let's look at these molecules and apply a similar logic. So for a start, we could put them into pairs. For example, X and Z are both alkanes, so they would have CnH2n plus 2. They've got the same general formula. And W and Y, they're not both alkenes, but they do both have the general formula CnH2n, because remember we said about that, removing hydrogen for cyclic as well as alkenes. So then we just do our counting. It turns out that W and Y do have the same number of carbons. They both have 6. So W and Y are isomers. If I were to look at X, however, 1, 2, 3, 4, 5, that has 6 carbons. But Z, 3, 4, 5, 6, 7 in total has 7. So it is not an isomer. So it's useful to remember for every double bond, then you're going to take off 2 hydrogens, or for every ring. And this is true for C double bond O as well as C double bond C. So for example, these 3 molecules here, I can don't actually need to count the hydrogens. I don't need to draw them out because I can see that each one has 6 carbons. Each one has 1 oxygen, and each one has some kind of double bond, whether it be a CO double bond or a CC double bond. That means that all of these isomers will have the same formula, molecular formula, C6H12, so it's CnH2n, and then an O. Finally, we'll just have a look at a couple more questions. What do we have to do if we've just got names? Again, do we need to draw all these molecules out just to know which of these has not got 10 carbons and 22 hydrogens? They're all alkanes, so they will all have a general formula of CnH2n plus 2. There is no need for me to sit and draw the formula to work out that that's how many hydrogens they have. They all end in ane. Job done. So all I need to do is just check how many carbons they have. So the first one, oct, means 8, dimethyl means 2 lots of 1 because a methyl group is 1, so that gives me 10. The second one, I've got hept, which means 7, and I've got tri, so 3 lots of 1, so 7 plus 3 gives me 10. The third one, I've got hept, which means 7. I've got prop, which means 3, that's 10. And the last one, I've got pent, which means 5, and I've got diethyl, so that's 2 times 2. 4 plus 5 is 9, so that is my odd one out. So all I have to do is know my prefixes, count the carbons, don't bother counting the hydrogens, they will look after themselves. Now let's look at a very similar question, skeletal formulae. This one is so quick and easy to answer. Again, I don't need to count anything because if I look at A, B and C, they're all cyclic. D is not cyclic. D must have a different number of hydrogens, even if they all have the same number of carbons. So D is definitely not a structural isomer of the other 3. Finally, let's look at how we can work out possible structural isomers. We've already kind of done it a little bit. So we can change the length of the chain and we can change the position of the functional group. So we kind of just do it in order. The easiest thing is usually to change the position of the functional group. So we've got C4H9Cl. Don't worry about again thinking, oh, I've got to count all those hydrogens. No, you don't. It's saturated. It's got 4 carbons. Let's put a Cl on the first one. 1, 2, 3, 4, 5, 6, 7, 8, 9 hydrogens. Next one I can do is simply move the chlorine. Put all my hydrogens in. Obviously, if you're doing it, you would draw all the hydrogens out. So far, I have got 1 chlorobutane and I have got 2 chlorobutane. I can't go any further with moving the chlorine because if I move it onto the 3, that's exactly the same as putting it on the second carbon. So the next thing I'm going to do then is make the chain shorter. So I can go 3 carbons in a row. My methyl group must go in the middle. And then I have options about where to put my chlorine. So this first option, let's put it on the first carbon. Then we can name that. So this is going to be 1 chloro, if you like, 2 methyl. Not strictly necessary. Propane. And then I can do the same again. 3 in a row. Methyl has to go in the middle and I can put my Cl there. Lots of people tend to sort of, I don't know, forget that you can put more than one thing on a carbon because even if it's in the middle of the chain, it's got 2 spaces on it. And so that one would be called 2 chloro, 2 methyl. Propane. Now you may be then tempted to start trying to put chlorines up here on this carbon, but all you're doing there is it still could be part of the main chain because that would still be 1 chloro, 2 methyl. If you put it there, all you're doing is sort of like changing where you're counting the main chain from. So be careful on that one, that you don't invent lots and lots of things just because you're drawing something wonky or at a different angle. That is where drawing your skeletal formulae will really help to show whether or not you've got different isomers.